Father, Mother, I see you have aligned with correcting the power factor. You believe power factor correction is important to deliver as much real power to the load as possible. Itachi, just promise me this. Always remember that PF correction is usually done by adding a capacitor in parallel with the load. Even if our philosophies differ, this will make power factor close to unity. Also, I am proud of you. You are truly a kind child.
Okay, so let's move to the discussion of power factor correction. So earlier, we had some definitions of power factor and how is it done. So as a recap, power factor correction is the process of increasing the power factor without altering the voltage or current to the original load. So again, increasing the PF power factor, okay, without changing any of the voltage or the current going to the load. So what is the importance of doing this? So if power factor is high, that means most of the real or useful power is being delivered to the load. Okay. So how is it done? So as Itachi's father said, or Gaku said, the power factor correction is usually done by adding a reactive element, usually it is a capacitor, in parallel to the load. And the inductive load is modeled as a series combination of the inductor and the resistor. So this capacitor being placed in parallel with the series combination of the inductor and resistor. Let's move to the example. So solving for power factor, involving power factor correction. Okay, so we have this example when connected to a 120 volts RMS 60 hertz power line, a load absorbs 4,000 watts or 4 kilowatts at a lagging power factor of 0.8. Find the value of the capacitance, okay, to raise the power factor to 0.95. So our goal is from 0.8, we move up to 0.95 power factor. So what is the value of that capacitor? So we're looking for the value of the capacitance here in order for us to achieve 0.95 power factor. So let's solve. Okay, when power factor is 0.8, so our angle using arc cosine theta is equal to 36.87 degrees. So in your calculator, you can do this. Arc cosine, then 0.8, then you'll have your angle. Next, let us solve for the apparent power, right? Apparent power is equal to real power over power factor. So we have 4,000. This is fixed, right? Fixed. Divided by 0.8, our current power factor. So apparent power is 5,000 volt amperes. And let's solve for the reactive power. So it is apparent power sine theta. So we have 5,000 multiplied by sine 36.87 degrees. So our reactive power, okay, is 3,000 bars. So now, what will happen if our power factor is 0.95? Okay, if power factor is 0.95, okay, let's solve for the angle. So cosine theta 2 is equal to 0.95. So 18.79 degrees by using arc cosine. Okay. As you can see here, the angle is reduced from 30 plus going to 18, right? It's closer to 0 or x-axis, right? Because our goal is to have a power factor of 0.95, so higher. Therefore, it will be closer to the real part, right? So proceeding with the apparent power. So we have, again, we'll be using 4,000 because it will not change, right? Real power. So 4,000 divided by 0.95 as the new power factor. So we have 4,210.5 volt amperes. Okay, let's solve for the new reactive power. So reactive power is equal to apparent power sine theta. So 4,210.5 sine 18.19 degrees. So we have 1,314.4 bars. So that is the new reactive power. So we need to get the capacitance, right? So first, we need to get the difference between the new and old reactive power because this is due to the parallel addition of the capacitor to the load. So this one. So the reactive power due to the capacitor is equal to Q sub C equal to Q sub 1, the old minus reactive power Q sub 2, which is the new one. So we have 3,000 minus 1,314.4. We have 1,685.6 bars. So this is the one being contributed by our capacitor. Okay. So we need to get the capacitance. So capacitance is equal to the reactive power contributed by the capacitor divided by 2 pi f multiplied by Vrms squared. So the frequency. So we have 1,685.6 bars divided by 2 pi times frequency of 60 hertz multiplied by 120 squared. So our capacitance is equal to 310.5 microfarads. So this is the value of capacitance needed to raise the power factor from 0.8 to 0.95. Okay. So in terms of power rating, of course, we need to choose a voltage rating higher than what's given. For example, if we have 120 volts RMS, so if you're going to convert it into peak, around 170 maybe, so choose at least 200 volts uh, voltage rating, right, to be safe. But in terms of the value of capacitance, so here we go, we have 310.5 microfarad.